Hey, kid! Give me one of my beers! Can you go get one?
What?
From the cooler. Can you go get it? No,
No.
not that one. The other one. Loretta! Hi, everyone. Welcome to End of Mission, the podcast where we can't introduce anything without sounding like depraved Southerners. I'm Paul, the pressure-fed astronaut. And who are you?
I'm depressed.
Welcome to End of Mission. Hi, everyone. Do we have any custodial things to start with? Oh, I hope the audio is fixed now. I think I've fixed it. I don't have to buy a new microphone. You have a new laptop that was made in this century.
Amazingly.
Yeah.
I still had to pull start it, but...
Yeah, well, mine's electric, so, still got to transition over. Any other custodial notes? This is coming out in August, late August, I think.
Cool.
So, yeah, it is still July as we're recording this. So,
Yeah.
This is great because we have to do an episode every 2 weeks next year. So,
Awesome.
yep. So
Looking forward to that.
Yeah. So today's mission is STS-57, and you can actually see it on the patch if you look closely.
Yeah.
You see it? It's 5 stars and the 7.
Yes.
Do you know what this is?
That is a box with wings.
Correct. And this shape here looks kind of familiar, doesn't it?
It's rather circular.
Look what I'm circling. What do you think it is?
Space a person be.
Yes. So, STS-57. We're on Endeavour again.
Yay!
This is the 56th flight of the Space Shuttle program, and just so you know, the next flight of the Space Shuttle is STS-51. The previous flight of the program was STS-55. The previous flight of Endeavour was STS-54, which we just covered. Yep. Very excited. This was not intentional, by the way. It wasn't intentional.
They would all just... You like numbers? How about 54, 55, 56, and 57? And yes, they are not related.
There's no relation, okay? Don't look any closer. So this is the 4th flight of Endeavour. It's got a few exciting mission highlights. This is the first flight of Spacehab, the module.
Oh, happy birthday.
Yeah. This is the recovery of Eureka, which was deployed on STS-46.
Cool.
There was an EVA to repair Eureka in tandem with the EVA activities like on STS-54, where they're preparing for the ISS.
Got it. Okay.
There's fluid transfer experiments, which is the reason I picked this mission. And there's a really good shot of the external tank that I like.
Ooh. Is it this one? This guy looks like he's doing geology stuff.
No, he's surveying. He's watching it come in. I learned some interesting things about this flight.
Okay.
So, what's in the payload bay?
Things?
A lot of things. You got a con cap, a lot of gas cans, Eureka, shoot! Spacehab, and then the fluid transfer experiments is in the mid-deck. So,
Exciting. What are we shooting?
that's a good question. We're to find out.
Yay.
Okay, so CONCAP is the Consortium for Materials Development in Space Complex Autonomous Payload.
That does not spell concap.
It does if you don't think about it.
It's like hum de cap.
So this is CONCAP 4. And guess what it's doing?
Is it it's hosting a consortium, a podcast? I don't know.
It's growing nonlinear organic crystals through vapor transport.
I should have guessed that.
It's the freebie, right? In the bingo free space. Crystal growth experiment.
Yeah. Oh, what's happening to this shuttle mission? Yeah, we should make bingo cards. That sounds fun.
We really should. I don't know what this is. Oh, I know what this one is. So let's go to the gas can. This is a gas can. So this is not the gas can we're talking about right now. So the first one is G22, liquid gauging technology experiment. It does 2 methods of determining liquid mass in tanks. Because right on Earth, it's pretty easy. You have like a dip or electronic sensor, but in space, microgravity, it's different.
Yeah.
This is going to be a theme
So
for all of this.
it's how much fuel you got in the tank if it's floating around in there.
Periodic volume stimulus. So I think they just shout at it.
Oh.
And then foreign mass injection method. So they put a plunger in and it's like, okay, well, it reacts this way. That's how much is in there. I couldn't find anything.
Threw
on
the
this.
cigarette inside of it, and then it lit up, so we know there's fuel in there.
There was, at least, yeah. So pictured here is G324. Can do.
Nice.
So
Love
this-
that response.
Yeah. So this takes 1,000 photos of Earth for students to make observations of global change. So to compare it to Skylab pictures.
Oh, okay.
It's also flying 350 student materials experiments.
Gosh. Think you got enough?
Yeah. I think this is part of it. Okay, for the record, I don't remember most of this. I started working on Magellan and Mars Observer, so I'm kind of thinking about exploring and circumnavigating instead of gas cans. I'm sorry, everybody. Okay? I'm
You
so-
complete and total failure. Unbelievable. This is unforgivable.
Wait. Okay, so that's not it. Okay, never mind. I'm done. Again, I should have looked through this before I did this. So G399, insulin tagging and artemia growth experiments. So they're figuring out how you can tag insulin in brine shrimp. Like
Cool.
see how it moves. G450, multiple experiments with 6 experiment containers. One has solidification of saccharin and cryogen transfers. So saccharin is sugar, I think.
Okay.
And then cryogens, of course, is liquids, cold liquids. 2 and 3 are bacteria and radiation plus 0-point energy experiments.
Ooh, that sounds exciting. Isn't that what Syndrome used in The Incredibles?
Yes, but mostly 0-point energy has to do with virtual particle antiparticle annihilation. Not what's
Right.
Not stretchy people and monologuing. Sorry, no capes. So 4 is electrode occlusion, bubble formation, and microgravity bonding. I couldn't find anything on this. I'm reading from the mission press kit. I was trying to go through this as fast as I could because I don't care about these experiments that much. I'm sorry.
Yeah.
So 5 is osmosis, reverse osmosis, and radiation experiments. And then 6 is, shockingly, a crystal growth experiment.
They grew crystals on the shuttle? I didn't know this.
I know. It's amazing, isn't it?
Mm-hmm.
G452 is... brace
Crystal
yourself.
growth experiments.
Gallium arsenide semiconductors. So then we have G453, semiconductors superconductor experiment. So
we're growing the crystals from one experiment with the other experiment.
Yes.
That's pretty cool.
G454, another crystal growth experiment, studies indium, gallium, arsenic from vapor phase under weightlessness. It's crystal growth experiments in space. We just can't escape doing this. You just can't do that. You gotta have. It's like maybe it's like a good luck charm. It's like if you don't bring this, everyone will die. I don't know.
There's some OCD person in the who's like creating the manifest, and it's like you have to put at least 3 different types of crystal growth experiments, otherwise the mission will fail.
Yeah. You have that guy, and then you have G535, which is a pool boiling experiment. So you don't swim there. So it observes heating and vapor bubble dynamics associated with bubble growth and collapse and subsequent bubble motion. So
they're playing with bubbles.
They're playing with bubbles on the space shuttle.
That's awesome.
It is pretty cool. Again, I could find nothing on this. G601, high frequency variations of the sun, analyzes rapid variations in solar flux.
Okay, that's pretty cool.
It is pretty neat. Some of these are really interesting experiments. I just can't find anything on them, and those weren't the primary reason I picked these missions. Sorry.
Mm-hmm.
G647, configurable hardware for multidisciplinary projects in space. Champs. What do you think they're doing?
Oh gosh, I just read the next.
It's and that's this one. This one's Champs. I think this one's Champs. So
Look at this.
Yeah. You can see the metals on them. Growing. So it's crystal growth using liquid phase electroapataxy, which uses an electrical current to regulate crystal growth.
Just more crystal growth.
Yeah, you just cannot escape it. Then you have a gas ballast payload. And then you have the sample return experiment. So it's going to sit on the ballast, and it's quantification of extraterrestrial and orbital debris in payload bay. So pretty much it's stuff's going to hit it, and they want to see what's actually hitting it.
Okay.
And then the secondary experiment on that is comet dust sample collection concepts to see if they're going to do a comet sample returns, which that they're probably preparing for Stardust at this point.
Would they? Does that timeline make sense?
Because this is 93.
Okay.
This is about right for Stardust was early 2000s, but it was launched before Genesis. So this is about right for that.
Okay.
So we have Eureka. We'll talk more about this in STS-46. We might do a side special on it. This is the European Retrievable Carrier. That makes sense.
What is it retrieving?
It's kind of like LDEF.
Oh, okay.
Yeah. So it's a 4.5-ton, 9,900-pound retrievable microgravity experiment platform like LDEF. It was launched by Atlantis on STS-46. So, what do you think's on board?
Protein crystal growth experiments.
Yep. Exobiology and radiation assembly, multi-furnace assembly, automatic mirror furnace, surface forces adhesion instrument, high precision thermostat instrument, solar... Wait, is there another slide? No, okay, never mind. Again, I should have looked at this beforehand. Solar constant and variability instrument, solar spectrum instrument, occultation radiometer instrument, wide-angle telescope, time band capture cell experiment, radio frequency ionization thruster assembly. So it's like little Teflon thrusters. It's actually pretty cool. And then the advanced solar gallium arsenide array. That's the solar panels.
Sounds awesome. That's a cool way of saying solar panels.
Yeah, it's a solar panel, basically. Yeah, it's you have the shuttle. You can launch science payloads and bring them back down. This is a smart thing to do. It's a shame we still don't do this.
Yeah.
It really does suck that we don't do stuff like this. It'd
be hype.
I have a business idea. Because I've heard
We'll talk later.
Because I've heard complaints that one of the problems with the ISS, while it is a longer-term microgravity science platform, you can't really return experiments that much. And even if you do, it's like 6 months later versus 2 or 3 weeks.
Uh-huh.
And ISS is in a locked orbit, kind of like... this is kind of like Comet Meteor from SSI. Kind of like that.
Mm-hmm.
And I think the Europeans are working on one, so we got to beat them.
Okay. We'll talk about this later.
We'll talk about this later. If you're interested in this and have millions upon millions of dollars, email me. Just saying.
Shoot.
Superfluid helium on orbit transfer flight demonstration.
Well, you have extra letters there, right? You have it's shoot FD.
Well, that's just the full title, but it's superfluid helium on orbit transfer.
Oh, yeah. So it's the nickname as opposed to the Christian name.
Yeah. So as you can see, it's on the bridge. It's one of those kinds of experiments. I discovered this experiment was on the flight after I started researching it. Again, I pick missions based off 1 or 2 things I think are interesting, and then everything else is incidental. Remember, I picked STS-54 because the crew photo was Star Trek.
Yes.
So this experiment is 9 years in the making. They started working on this in literally 1984.
Oh my gosh.
The experiment is to demonstrate methods for resupplying superfluid helium on orbit to space telescopes, because like James Webb has liquid helium on it to keep the infrared part cool.
Oh, right. Okay.
Well, eventually that'll all boil off, so you want to replace it. Instead of getting rid of the telescope, you replace the helium.
I'm sure we could just spend another $12 billion or whatever, how much it cost?
10.8. Well, technically you could build it easier now that you've built it, because half of James Webb was just developing the technology to make it work.
True. So that'd be like, we have another $5 billion we could chuck into it.
Yeah. NASA's definitely got that kind of money.
Yeah, easy.
So it's got 2 doers with complex cryostats containing helium at 4.2 Kelvin.
What are these doers?
Doers are just cryogenic containers.
Oh, okay.
That's what they're called. They're called doers. I've seen one for liquid nitrogen. They made ice cream once at the U of M with doers.
Oh, okay, that's pretty cool.
Yeah, it is really cool. And the cryostats are basically methods of mitigating the like loss of helium. Because remember, 4.2 Kelvin. The universe is at about 3 Kelvin.
This is really cold.
Minus 452.1 degrees Fahrenheit. So a Minnesota winter.
Yeah, typical Minnesota winter.
So what they use is so liquid levels and fluid positions are measured using superconducting liquid level detectors, because at those temperatures, that's where you get superconductivity. Which
That's awesome.
you ever see video of superfluid helium moving?
No.
Oh, it's really so. You have a dewar, right, container of it, and you have the helium, right,
Mm-hmm.
and it's liquid. Then they have like a little spoon of it up here, right, and it climbs out of the cup and goes back into the main container. It is the coolest thing ever. It is really
like, oh,
weird.
look, it's trying to escape.
Yeah, it is. Yeah, super fluid stuff at those temperatures. It's really interesting. If you ever take physics classes on this, it's really interesting. So they use superconducting liquid level detectors, heat pulse mass gauging calorimetry. So pretty much they send a little electrical current in to see how hot it is, and based on how much it heats up, you can kind of guess how much is in there, right? Because it's thermal mass.
Right.
And then liquid vapor discriminators, so it's racist. So pumping is done using the thermomechanical or fountain effect, which is unique to superfluid helium.
Tries to escape.
Yeah, it tries to escape and you direct it into the other tank. So it's basically a porous cup with a heater. So they heat it up and it kind of fountains, which that's
awesome. So it's basically like a little helium volcano.
Yeah. And so use liquid acquisition devices, LADs, those use surface tension. We'll see more of these. That's what the main liquid experiment I picked this flight for has, and there's actual pictures of them. So it's basically it's little veins in the tank, because remember, on Earth, right, under 1G, liquid stays down, right? But in space, in microgravity, right?
Yeah.
The propellant climbs to the walls of the tanks.
Oh, okay.
So how do you get the propellant out of that?
You suck it from the walls of the tanks.
Exactly. So you put in veins or meshes. And we'll talk about this with FAIR, the actual experiment, and it clings to that, and they use that to hold on to it. So it doesn't form like bubbles here. It just becomes vapor instead. You ever see any video of like propellant tanks in space? There's one or two that exist.
Maybe, but I forgot.
Like, there's one of a Falcon 9 second stage. I think it's the kerosene tank. And you can see the propellant, and then the engine shuts down, and then it just kind of floats up.
Okay.
Yeah.
It's pretty cool.
Yeah, so they use surface tension to gather liquid in the tank and direct it to the inlet. The starboard tank has a mesh. The other one has 60 radial veins.
Oh, so it's a compare and contrast.
Yeah, they're testing out. So they test out multiple methods of transfer, right? Vein and sponge method or screen channels.
Got it. Okay.
And there's a whole paper, the link is in the description, that talks about how do you make this thing so it doesn't lose the helium.
I imagine that's probably a pretty difficult challenge.
It was a very difficult challenge. So, let's go to Space Hab, which has lots of experiments inside. So, there's commercial material science experiments. So there's equipment for controlled liquid phase sintering experiments, Eclipse. So its metallic powders are consolidated into a metal at 50 to 75% melting temperature to make metallic composites with great wearing properties. So right, wearing is like, you move it around a lot, you grind it, it doesn't wear down.
Oh, I thought it was put it on like weird clothes.
It does look good on you. You just look really weird. Before we go farther, so this is the Space Hab module, right? It's got a little tunnel. It's got, the module, again, it's like a sardine can versus the really long Space Lab module.
Right.
But it's basically the same setup. You have racks on the sides. And this is actually all the experiments that are in the Space Hab. These are all labeled. These are all the experiments.
Jeepers.
Yeah, so this is the tunnel looking forward, right? So Eclipse, if you're looking forward, is this.
Okay.
So that's Eclipse. And you can see there's a bunch of different experiments on there. We're gonna run through all of these because I'm not gonna do all of them. This has, I think, 70 slides.
Oh my gosh, dude.
So there's Eclipse. Is this Eclipse? No. Yes, it is. This is Eclipse because it's got argon quench line. This is a little furnace.
Okay.
I think. Yes.
Cool.
Yeah. Isn't that cool?
It's a little oven. Yeah.
It's a little oven. Right? Then you have... that's not it. They have gas permeable polymeric materials. Its monomers and activators are mixed in a commercial refrigerator incubator module to form membranes that can be permeated by gas.
Okay. So it lets gas leak through, but stops all the other stuff.
Certain types of gas go through. Yeah, it's useful for industrial applications, like gas masks.
Right.
Yeah. Then you have investigations into polymer membrane processing. That's this guy.
Okay. Set up a little maze for the polymers to try and solve.
Yeah. So its mixed solvent systems are evaporated in microgravity and controlled by induced convection for porosity and chemical properties. It's useful.
I like that the other things you have to use on it are also duct tape and a towel.
Yes. Hey, always know where your towel is.
Yeah, true.
And then we have, that's not it, but that's the next one. So we have liquid encapsulated melt zone. Float zone process is used to grow large, pure, homogeneous, and structurally perfect crystals, Jesse. Okay? Perfect. Pure.
99.1% purity, Jesse.
I started watching a TV show on Netflix called Sneaky Pete, and Bryan Cranston's in it. It's from 2015, but that's Bryan Cranston. It's Walter White. Wait, this is the experiment actually. Yeah, so they have indium bismuth rods. They're gonna melt them in this and see how it they're gonna grow some pure crystal. Yeah. Then we have zeolite crystal growth. So zeolites are complex silica arrangements and alumina which can absorb elements or compounds selectively. So this would be good for cleaning stuff up out of your blood.
Oh, okay. It's a picky eater.
It's picky, yeah. Come on, eat your vegetables. Then you can have the
also,
pure.
Sorry. Just zeolite is a cool name.
That is a very cool thing. Yeah, zeolite. It's a very 90s thing too, right? Zeolites.
Yeah. Mr. Bond, the zeolite crystal growth.
Yes. So you have a furnace module again. You'll see pictures of it as we go. Mm-hmm. So that's the zeolite module. They're growing crystal, counting dust. What else is there to do in space? There is nothing else you can do.
Well, go back to the commercial float zone, right?
Yep, there we go. So then we have life science experiments. This one is astroculture.
That's awesome.
This is the second.
A lot of great names.
Oh, you gotta love the naming on these things. So this is actually the second astroculture experiment. The first one flew, I think, on STS-53. So this is a self-contained hydroponic system designed to supply water and nutrients to plants in space. Because the idea is if you do long enough space missions, it's actually more mass efficient to grow food up in space.
Oh.
Based on the research done in the early 2000s that you can find on atomic rockets, it's somewhere around 340 days. Where if your mission's longer than that, it's actually more mass efficient, theoretically, to grow food on your mission than it is to carry it with you.
Gotta go farming in space.
Yep. As shown in the documentary film The Martian.
Mm-hmm. Yes.
So in this one, they're testing out the means of depositing nutrients into the plants. So it's got two growth chambers with inert material that serves as a root matrix, right? It's kind of like it's like when you plant stuff. They're testing the water supply system for that.
Have you ever considered water gun? Just shoot the water at them.
Like a squirt gun?
Yeah.
That was invented by a guy working on the ohms.
Really?
Yeah, I think it was. Yeah, he was working on ohms, and he's looking for different pressurization systems for that, and he came up with the super sucker.
So,
Your taxpayer dollars at work, guys. Just remember that. So then we have, so this is just generic. Again, so this is the other side. So you're looking aft. I think you're looking aft. Yeah, this is aft.
Oh.
Yeah, this is aft, because if it was forward, you'd have the middle spot with like the camera holes. So this is looking aft. So this is the rest of the experiments that are life sciences. You have BioServe Pilot Laboratory. So there's 2 sets of experiments for bacterial products and processes. The first is Rhizobium trifolia's symbiotic relationship with legumes.
Sounds like a book title.
It is. That's my autobiography, actually.
Mm.
That's my pen name, Rhizobium trifoliae. Look for me on Amazon. The second involves growing E. coli in microgravity.
Oh.
Yeah. There are 40 modules on this flight.
Bringing E. coli up into space?
Yes.
So E. coli gets to go up into space before I do.
Yeah. Just remember, E. coli gets to go to space before you. What does that say about you?
I feel bad.
Also, I learned that E. coli really grows well in about 400,000 G acceleration. Because you get those little medical centrifuges, and you spin those. That actually has that it gets simulated to about 400,000 Gs, and they discovered E. coli grows really well at high gravity.
Bring on the G's.
Come on, I can take it. Let me grow more. Ha
Which I lift, bruh.
Yeah, do you even lift? So then we have the commercial generic bioprocessing apparatus with 27 experiments: biomedical testing, cells, organic separation, protein crystal growth. Then you have the physiological system experiment that involves 12 rats and tissue repair.
Exhilarating.
It is
12 whole rats.
I didn't get any pictures of them. I think their cages are probably over here.
Okay.
I think that's their cages. Again, I can never find pictures of them. I think it's a HIPAA thing. I don't know. You can never find pictures of the rodents.
They're protected citizens.
Yeah. So then you have Johnson Space Center has some investigations they're doing. 1. Application-specific pre-programmed experiment culture system. It's a cell-growing maintenance units that can operate for 14 days. It's this. Aspec.
It's a box.
It's a box. Yeah.
Really exciting.
Then you have the charged particle... That's not it. You have the charged particle directional spectrometer. It detects and records different types of nuclear radiation that hit the spacecraft.
Got it. Okay. Kind of like that other one.
Yeah. Then you have the human factors assessment. It's, hey, we're using Space Lab now. Can people actually use this? Like, can you put your hand in places and turn knobs and instead of, why is the button there?
Yeah. Yeah, we put the button on the outside of the spacecraft. You can just grab it real quick.
Yeah, just like in the core. What's it doing there? And then you have neutral body posture. So, you know how people float, right? Kind of your arms out, legs kind of in a certain spot?
Mm-hmm.
They're
T-pose to assert dominance, yeah.
You kind of like that. Well, they're just pretty much seeing how that impacts people because in spaceflight, you actually grow by 2 inches. Because your spine relaxes.
Oh, the reason why I'm only 5'9" as opposed to 5'11" is because my spine is stressed?
Yeah, because your spine is stressed. Again, this would improve your Tinder matches. Just go to space, grow 2 inches. You don't need that leg lengthening surgery that other people do. You just need to go to space to get 2 inches taller.
Yeah, why do distractions when you can go to space? One's way easier than the other.
Yeah, space is so much easier.
Yeah. Gosh.
And then we have tools and diagnostic systems. So they're testing out soldering and desoldering electrical circuits while assessing foot restraints for precision work. Pretty much, if we have to repair a circuit in space, can you actually do that?
I mean, I could barely do that here on Earth, and so in a zero-G environment, which everything's going to be trying to move away from me when I touch it, that sounds like it'd be a frustrating nightmare.
Yeah, so that's what he's doing right here, is he's testing out soldering iron in space and seeing if it actually works, and if you can actually do it.
Okay.
And then we have the Space Station ECLSS flight experiment. So they're testing out 3 pieces of water recycling hardware, a bellows tank, gas water phase separator, and 2 filters on the little astronaut's room.
Delicious.
And they're using potassium iodide to simulate a contaminant in that, right? Because if you want to recycle the water to drink it again, it should be clean.
It should be clean going in, or should it be clean going out?
Going out.
Yeah.
Wastewater. Like at the beginning of Waterworld. You know what I'm talking about.
Yes.
And this is another just picture of the experiments.
Yep,
there it is. So then we have microgravity measurements. We have a 3D microgravity accelerometer. It's measuring deviations from zero gravity at various locations inside Space Hab. You're always doing that. Then you have SAMS, which is also measuring low-level accelerations by experiment operations. So actually, SAMS is... I think it's... Wait. It's not this one, but it's one... I think it's on the forward experiment rack.
Oh, the other side, okay.
Yeah. I think it's in one of the pictures of the inside of the shuttle, but yeah.
Okay.
Science experiments in space. Wow.
Who'd have thought?
Astroculture.
Astroculture.
That's a cool name.
Get astrocultured.
Yeah. Got that. So we have one mid-deck experiment, and you can see where it is, right? It's this guy.
This guy with the cylinders.
Yep. The spheres.
Or spheres.
Spheres. Geometry. Oh no.
Cassette tape.
Oh
no.
Got your 8 tracks out. I mean, what else are you going to do in space, right?
It's going to break.
So this is Fluid Acquisition and Resupply Experiment 2.
Ooh.
Yeah, the
It
sequel.
was so good, they got the sequel.
Yep. So the first one flew on STS-53. That's right. That's that mission.
Okay.
So Fair 2 is to establish vein device performance. I can't spell. Performance. It's vein device performance limits versus expulsion rate and acceleration environment. So pretty much they're testing out, can you build veins inside propellant tanks, transfer fluids between them under different environments?
Okay. But again, just testing more fluid transfer.
Yeah. This will be the first orbital refilling of tanks with vein devices. Ever.
Okay. Ever.
Yeah. So the goals here, there's 3 of them. Demonstrate low gravity operation of vein type liquid acquisition device during tank expulsion. 2. Evaluate vein capability to orient ullage bubble over tank vent during fill process. 3. Demonstrate static behavior of liquid under low G conditions and dynamics under acceleration. So pretty much, what do the fluids do when you're not moving or when you're moving?
When you're looking at them versus not looking at them?
Pretty much. So you have a liquid acquisition device. You're going to push ullage gas into it, and they're going to move it from one tank to the next, and they're going to see what it does.
Okay.
They want to see if they can orient the bubble of ullage, right? Because you're going to have a bit of gas in there. And there's pictures, don't worry.
Good.
So in microgravity, fluids cling to the walls of propellant tanks. We discussed this. For resupply capabilities, lads are used to collect liquids on veins and meshes so that when pressure is added to the tank, the liquid will follow the vein into the tank and out through the valves, right? Where it's supposed to go.
Okay.
That's what they're doing. So this is a diagram of it. So you can see there's veins, right? You can see those?
Ah, yeah. Almost look like little filaments in there.
Yeah, that's because they're acrylic. And I actually have some pictures of Cassini's veins because they use those on Cassini when we get to that one. Yeah. So what they're doing is going to fill the tank from here, right? It's going to collect around the standpipe, the central pipe, and then it's going to kind of cling to the veins.
Okay.
It's the same like a wicking process, right? Kind of like with candles, right? Because it's that they have the wick, and then you have the wax, which will melt and then get pulled into that to burn.
Okay.
That's how that works. So when they fill it all the way, it'll have a bubble, and then to see what that does.
Is the bubble moving?
Exactly. So then we have, right, one of the tests, and the Weber number has to do with the density and viscosity as it's flowing between different things. That's what a Weber number is. So to test out, where are the other bubbles? What can you do? How do you if you cover the vent, if you don't cover the vent, that sort of thing.
Okay.
It's fluid mechanics. It's really cool. It's got really pretty pictures. That's why I picked this.
It's green.
It's blue.
Yeah, it's a bluish green. Yeah.
It's a bluish green, yeah. Wow, what's your screen calibrated to? Jeez.
Got a new computer, okay? Gosh.
Yeah. Again, this is the reason I picked this mission for this, because I did for my senior design project in college, I did a resupply mission for Mars missions. So I got to read about all of this.
This looks awesome.
It's really cool. I mean, I have a lot of pictures of it. You can see there's bubbles, too, to see what those do.
Yeah.
Because you want to ingest vapor, of course. That'd be bad.
Yeah, it's like getting air in your lungs.
Yeah.
Not in your lungs, in your blood.
Yeah. So who's flying this mission? You recognize at least one or two of them, right?
Yes.
Which two do you recognize?
I recognize Janice.
Yep, of course. We get a lot of her missions.
And shoot.
Covering.
Yeah.
Ron Graves on yours. I'm recording next.
What?
He's on the next mission we're doing.
Looks very different.
Well, it's age,
Yeah.
I think that's him. So, here's our crew. Here's our brave
Yep.
crew.
Oh, yep.
So our commander is Ronald J. Grabe. He was born June 13th, 1945. He's from New York City. Good for him. He's an Air Force pilot and engineer. He did a lot of work with the British for teaching them how to fly. And he got his engineering degree at Technical Universität Darmstadt in West Germany.
Hilarious.
Show off. He's from Astronaut Group 9. This is his last of 4 flights. So his previous flights were STS-51J, STS-30, and STS-42.
Yeah.
And his flight photo is for STS-30.
Yep. So you're going to see it again.
You're seeing it for the next one. Our pilot is Brian Duffy. He was born June 20th, 1953, really close to Ron. He's from Rockland, Massachusetts. He's an Air Force pilot and systems manager with a master's degree from USC. He's from Group 11. This is his second of 4 flights. His previous flight is STS-45. He had a lot of development on testing of displays, procedures, and software that's used on the shuttle.
Okay.
Yeah.
That's pretty cool.
It's cool. So Mission Specialist 1, our payload commander, is George David Lowe. He was born February 19th, 1956. He did die on March 15th, 2008 of cancer.
R.I.P.
He's from Cleveland, Ohio, so that makes a lot of sense. He's a mechanical engineer with his MS in astronautics from Stanford. He's from Group 10. This is the last of 3 flights he's going to do. His previous were STS-32 and STS-43. Now, for those of you who recognize that name, his father is George Lowe, who was the Apollo spacecraft program office manager. Him. Yeah. A bit of a show off here. It's like, they made fun of him. It's like, just going to call your dad now? Oh, my dad was part of the Apollo program. Yeah, it's like, this is just nepotism. It's nepotism. Yeah. So, our MS-2 flight engineer is Nancy J. Sherlock. Now, it's now Nancy J. Curry Gregg, but before she became Curry Gregg. So, just to be clear. Yeah, she got married, so it's Nancy Sherlock. So, I bet she got a lot of jokes about that. Yeah, she was born December 29th, 1958. She's from Wilmington, Delaware. Is that even
Delaware?
Is that even a real state?
I thought it was just a place that companies go to.
That's where Joe Biden's from.
Yeah.
She is an Army pilot and industrial engineer. She's got a PhD. I don't remember where she got it from.
Someplace. Presumably an accredited university.
We hope so. She's from Astronaut Group 13. This is her first of 4 flights. She's a helicopter pilot. So.
Oh, wow. Different.
Yeah. She worked robotics, space, and life sciences at Johnson Space Center before doing the mission. So, that's pretty cool.
That is pretty cool.
Mission Specialist 3 is Peter J. K. Wissoff. He was born August 16th, 1958, which this means this is coming out near his birthday. So, happy birthday.
Happy birthday.
He's from Norfolk, Virginia. He's a physicist with a PhD from Stanford. He's also astronaut group 13. This is his first of 4 flights, and all of his work is on short wavelength lasers. Everything. I was just reading his Wikipedia page, right? Because that's how I get all my information. And it's like, so for his graduate work, he was working with lasers for this application. Then his PhD work was on lasers for these applications. Then at NASA, he worked on lasers for these applications. It's like, dude, you love lasers, okay?
He's an astronaut who loves lasers going into space.
Which, that is pretty cool. He's an astronaut who
That's
works.
awesome.
Yeah, that's like the ultimate. Yeah, I want to be an astronaut and work with lasers. And then mission specialist 4, of course, is Janice Voss. She was born October 8th, 1956. She died of cancer in 2012. She's from South Bend, Indiana. She's electrical engineer with a PhD in aero and astronautics from MIT. Very accomplished. Astronaut Group 13. We last saw her on STS 83/94. She read the book A Wrinkle in Time, and that's what made her want to be an astronaut. And actually, there's a picture of her on STS 94 where she's reading it. Yeah, I don't think I included that in the episode. I wanted to bring it up here. Because, you know, it's not like we can't not talk about previous missions.
No, never talk about it.
Yeah. Who are these people? What's going on? This is quick. It's going a lot faster than I thought it would. So the original launch date was going to be in mid-May 1993. That was pushed to June. They wanted to delay it for a daylight liftoff and daylight landing.
So they pushed it off by a couple of weeks?
Yeah. Then the second launch date was June 3rd, 1993. But as they were doing inspections, they found a misplaced inspection stamp on a spring in engine 2's high-pressure oxidizer turbo pump. So they have, of course, go, if that's not in the right spot, let's open up the engine to make sure it's actually in the right place and correctly inspected before doing this.
Yeah, that sounds kind of important.
Yeah, what was... And then, as they're rolling it to the pad, they hear a big bang.
That's a good sign.
Yeah, that's the thing you want to hear on your multi-billion-dollar spacecraft is a bang.
Yeah.
What was that?
Yeah, it probably wasn't important.
So that was a ball strut tie rod assembly in the liquid hydrogen line, which is like 17 inches across, right? That's the big, one of the big lines that was just settling into place.
Oh, I was going to make a joke that it was just, it's just settling, like a house, but I guess that was right.
Yeah. Again, just what is going on? You just hear this big... What was that? So then
I'm sure it's fine.
So this delays the launch by about 2 weeks, for obvious reasons. So the next launch date is June 20th, 1993, which would have been Duffy's birthday. But it was scrubbed at T-minus 5 minutes due to weather conditions at the transatlantic abort site.
Right, yeah. Weather conditions. And then they go back in and give him a birthday cake.
Yeah. Oh, it's scrubbed, come back. Happy birthday! We scrubbed it! We could have grown so many crystals! What's going on?
I'd rather celebrate my birthday in space, thank you.
Yeah. So the actual launch is June 21st, 1993 at 9:07 in the morning from pad LC-39B. This is the launch.
They're 7 minutes late from work.
Yes. The orbit they go into is 471 by 402 kilometers, or 293 by 250 miles at, 28.5 degrees.
Due east out of the Cape.
Yep. And fun fact, the frustrum, so that's the cone, on the right SRB, which you can't see here, flew on Artemis 1.
Oh, wow, okay.
So it's at the bottom of the Atlantic right now.
A long history. Godspeed.
It also flew on STS-94. So bring it all back. Gosh. It all goes back together. Everything is connected. Right? It's that meme from It's Always Sunny, right?
Yeah.
Which I've never seen that show, but I know that. This mission is also extended by 2 days due to weather conditions. Oh, darn.
Dang it, I have to spend 2 more whole days in space.
Now, so the picture on the left is, so you can see that's the SRB at ignition, and this is the hold down bolt, right?
Mm-hmm.
So you can see there's a little bit of it that didn't go in the right spot.
Uh-oh.
That's not good. Yeah. I found images of this. I think it's cool. I think it's, because look, that's the SRB.
Yeah.
That's it lifting off.
That's the fire coming out of it at the bottom.
That's the explosion. Yeah.
Yeah.
So this is where debris hit it on the way up.
Okay.
And then the external tank had a little crack on the gaseous hydrogen return line.
That's a good thing, right?
No.
Oh.
Not really, but it's not fatal. But it's again, every anomaly should be recorded, so in case something bad happens, especially with foam on the external tank.
Yeah, you'll know. I like how also you look at the debris patterns, and it's mostly on the patient left.
Yeah,
Patient right.
Yeah, it's all over here. Yeah. But you can see mostly it's, here's the external tank. Hey, where's all the debris?
Yeah. Interesting.
Yeah, kooky. So this is the external tank after separation.
Cool.
This is a great shot. Because also you can see this is the SRB mount there. That's what's attached. And you can see like
you also see the orbiter attachment points.
Yep, there's the orbiter attachment, which is so cool. And this is, of course, SRB attached there. And then we have this, which is my favorite external tank shot from a shuttle mission.
Wow. That's cool.
It's a really nice image. It looks really good.
Very burnt.
It is very burnt. Well, again, aerothermal heating, and then you have the SRB separation motors here. And then down here you have the heat of, how many million pounds thrust?
Lots.
All right, so now we're on orbit.
Yay.
Look at that.
That's beautiful.
So, on the 22nd of June, the crew did talk to Bill Clinton on a phone call.
Oh.
There's
a quick call with the president?
Yeah, it's like, hey, I was going to do my Bill Clinton impression, but I can't do it on the spot. But they called him, they talked to him. You can find the video of it on YouTube. It's interesting. So then here they are doing some science.
Exciting.
Yep, there they are in the space hab and the old spare hoses and connectors. Science. Look at that. That's some science right there.
That's some. He's touching that science.
Yeah, good for him.
Mm-hmm.
Again, I always look for the weird shots of the crew.
The out of focus ones?
Out of focus, or just making a funny face, or going to Costco for the receipts. As you can see.
Yeah. Jeez.
I just love this, like 5 rolls of duct tape just ready to be used, just everywhere in the shuttle.
Well, yeah.
You never know when you need it. And then there's it's piloting, and then there's Nancy on the RMS. I like that shot.
It's a good shot.
It's a funny one. Kind of reminds me of Fear and Loathing in Las Vegas. You ever see that movie?
Yeah. Yep.
Yeah, it reminds me of that. Yeah. So let's go recover Eureka on the 24th of June. There it is.
It's a little small. Doesn't have a whole lot of pixels.
Well, it's very far away right now.
Oh. Okay.
Yeah. There are a lot of pixels in this shot, aren't there?
There are so many pixels. Yeah.
So there's actually
bigger.
So there's actually an issue with this. So it's designed to fold up its solar arrays and fold up its communications antennas.
Mm-hmm.
One of the communications antennas doesn't fold up.
Uh-oh.
But don't worry. They have a plan. They're planning for an EVA anyway. Yeah, kind of. Oh. So here it is being grappled by the RMS, as you can see.
Mm-hmm.
Which is, you can see, that's Eureka. You can see it's designed to be mounted in the payload bay, because that's the mount, the bottom here.
Yep, over on the left side.
Yeah,
right.
And this is the trunnion pin, so it locks into place on the shuttle. And
so it's going to be stuck in sideways.
Yeah, so it's going to be stuck in like forward, aft.
Right. So the solar panels are in line with the direction of the of the shuttle. And it's okay.
That's how it operates. Yeah, there's some close-up shots of it that were taken because I think that's pretty cool. So you can see like the solar array, how it's all folded up, all the mechanical devices for it.
Yeah, it's got little pulleys and whatnot.
Yeah, and here's the insulation that's just tacked on.
It's got a towel. It looks like.
Yeah, always know where your towel is. And you can see here's one of the experiments.
Just sticking out the side. Yeah.
Well, here's another one. Well, again, it's a space science experiment. You're exposing stuff to the vacuum of space, and you're going to see what happens to it.
Yeah, it needs to be outside where the space is.
Yeah.
Also, I do like the font for Eureka.
Oh yeah, that's cool.
That's cool.
That's really cool. Very 80s sci-fi.
Oh yeah,
I love it. So here's another shot of Eureka. There's, again, I think that's a grapple fixture or something.
Presumably.
It's one of the experiments that's on board. And here's more of the solar panels, just because they're cool.
Yeah.
And here it is being loaded into the space shuttle. So what was decided was they'll lower it in, because the RMS is providing power to the spacecraft right now. What they'll do then... No, it's not providing power because the connector was put in upside down. So that's
Murphy's Law, huh?
So that's why they can't retract the antennas. Sorry, again, I've been reading about Magellan and Mars Observer. I'm thinking about different disasters here. So the plan is they're going to get the EVA out and they're going to manually put the antennas back in place.
Got it.
So here it is being put in place with all the glorious pixels available.
Mm-hmm.
And you can see there's chute right there.
Ah, yes.
So there's chute, which is, again, really cool. The gas bridge is behind all of this.
Right. Okay.
So let's do an EVA.
Let's do an EVA.
So it's on June 25th, 1993. It goes for nearly 6 hours.
Just a quick, brief 5 hours and 50 minutes.
Yep. So EVA 1, Red Stripe, is George Lowe. EVA 2 is Peter Wissoff. And then Nancy Sherlock is on the RMS.
Okay.
So the original goal of the EVA was practicing for ISS on Hubble repairs, but now it's securing the dual antennas for Eureka, and then it can latch it into the payload bay and bring it back down. You don't want to make sure the tie downs can go down all the way, right? Kind of like at the back of your truck.
Gotta get the ratchet straps.
So a lot like STS-54, this EVA is to build experience and preparation for the Hubble servicing mission on STS-61 in December of that year, and work on building the ISS.
Right.
So the first set of tests were one astronaut's mounted to the RMS, and then they're pretty much moving the other one around like a large inanimate object.
Oh, okay.
Yeah. Kind of like I could think of as like those pizza spinner guy, like come get come here, the spinner guy. There's a sign, he's holding it. Like that.
Yeah.
And then it's the management of safety tethers while attached to the RMS, because you got to attach the RMS. What's the easiest way to move them around? What's the easiest way to use them? Can you lasso things, I guess?
Of course you can.
And then the last experiment is simulating fitting a large object to the payload bay. So it's an astronaut that's mounted to a foot restraint. That's the large object they're going to move around the payload bay, and they're going to mount them.
Time to get bolted into the back.
Yep. There we go. I'm tired of your stuff. I'm tired of you. That's it.
Bad astronauts get mounted to the payload bay.
I am tired of hearing about how cool your dad was for the Apollo program, okay? You're staying back here, okay? Don't make me turn the RMS around, okay? Go play with the super hoop. Don't go play with the super fluid helium, okay? Don't make me use that on you. Gosh. And they also practice working around with various tools like fastening bolts. Yeah, because again, ISS repairs, and that's a cool shot. So here they go. Here they are, playing with tethers. So again, Low, Red Stripe, Wissoff. Yeah, of course, here they are working on Eureka. It's like, what'd you say?
It's a candid shot.
Isn't that what it looks like? It's like, what?
It is. It's like, hey, did you know that my dad was in the Apollo program? Huh?
Hold the flashlight in another spot, kid. Gotta fix this. That's
it's
so
a
cool.
clinker.
So here they are again at work, working on Space Hat, and there's Space Lab. And so actually, the airlock is the connecting tunnel between Space Hab and the orbiter, of course.
Mm-hmm.
As you can see, the hatch is open here.
Oh, right.
Yeah,
Okay.
that's the hatch. And again, so here they are on the RMS, moving around, swearing at each other, I guess. Come on, fix it! No, put it over there! You know.
Give me the spanner. Dang it.
Yeah, come on. No, the other one. The other one. I want to move you around now. Yeah, so here they are.
No, my left, your right.
So I think they're working with safety tethers, clicking themselves to, because you can see there's the big long tether along the payload bay, and I think they're playing with the tether now on that.
Fun.
Which
Very
is
fun.
And you can also see how the RMS articulates too. You can see that.
Yeah.
Which is really cool. As much as I don't like flying and I'm afraid of heights, it would be cool to do an EVA.
Yeah.
It'd be really cool.
Well, you're not falling with an EVA. You let go, you're not falling.
That is quite true. You're just drifting away.
Yeah, slowly, but surely.
Inexorably.
Indubitably.
Yeah. But yeah, so here they are working on things. So there's the foot restraint in the right image. They're working on that.
Okay.
Yeah. You can see you got the safety tether attached, right? There it is.
Yep.
Yeah, but they're working on things. They're doing their experiments. They're doing their EVAs, which is really fun.
We're gonna long shift.
Yeah. All right. Yeah, we did all of our work. There we go. And usually when I pick these images, I try to go chronologically. And usually when they're uploaded into Space Wikia, where I get these images from, they should be chronological. They should be. I don't know how much chronologically they are, but they should be.
Let's just assume that they are and move on.
Yeah, so here they are again working with the tethers and shouting at each other. No, you do it! I have the high ground. I'm on the RMS.
You underestimate my power.
And then we go back inside. More crew shots. Look, they're doing things. And look, there's tape taped to the Velcro to the RMS.
I'd use the tape dispenser to tape this tape dispenser to the wall.
So there's Pilot Duffy doing his work in these 90s polos.
Gotta love the 90s polos.
So again, here we're doing the soldering experiment there.
Mm-hmm.
And we have, there's Nancy.
Sending email.
Yeah, or she's tweeting. And look at...
In the 90s, yeah.
Yeah. Look at that ancient technology.
Looks like my laptop.
Yeah.
You know,
that's what you
boxy and gray.
That's what you were recording on before.
Yeah.
There they are doing science in the Space Hab.
Very cool, very spacious.
That's a cool shot on the left.
Yeah.
Oh, so that's Sam's. See, there's the accelerometer. That's Sam's.
Okay. Hi, Sam.
Yep, there it is. I told you I'd find it. Just running these. Yeah, so there's where it's attached to. So that's Sam's down there as well. But yeah.
Oh, so there's more than one Sam's. Okay.
Yeah, so just, the mounts are in different spots. They connect in with the cable to measure accelerations.
Right.
Yeah.
Forgot that part.
Yeah, and there's Janice bringing in, I don't know, a cassette tape. I don't know.
Whatever it is that the 90s people do.
Yeah, science stuff from the 90s. And, you know, the Space Hab does look pretty spacious.
Yeah. From this angle.
I also suppose you're in microgravity, so it's easier to move around. You're not as annoyed. Because standing around in that, it'd get pretty cramped.
Yes. But they're elevated.
That's true. Here's Janice again doing some more, I think, RMS work.
Looks like it.
Yep, and then we're pondering things here.
How do cameras work?
Yes. Yes. Oh no. Oh, look over there.
What is that? What is that?
Save icons. Floppy disks.
Oh, floppy. Well, it is the 90s.
Yeah, but there they are. There they are.
Look, witness. Kilobytes of data.
Yeah. You could record so many experiments on that.
so much experiment.
And I think this red tube here is the air conditioning line.
I assumed it had to be something like that.
Yeah, because it goes through the connecting tube, so I'm assuming it's that.
It's the gaseous oxygen line as opposed to the liquid oxygen one.
Yeah. And then here we are. I think that's the sintering experiment we talked about before, and he's putting a screwdriver in it because why not?
It's a pencil sharpener. He's sticking screwdriver.
He's sharpening. This is the weirdest experiment I've ever done. And of course, sun's out, guns out. All right.
Yep.
Oh, is that?
I
think that's a timer.
It looks like it's a timer. Yeah, I was just distracted by the camera pointing at the duct taped hoses and wires and lines. And whatnot
yeah, everything is duct tape.
Well, that's why you need 5 rolls.
Yeah, that's half the shuttle payload mass. It's just duct tape.
Yeah, always have a spare duct tape experiment at the ready.
That's what it's for. So this is fair too.
Yes.
So this is the main event. It's blue.
It's blue. Why are you blue?
So you can see you have the veins here, right?
Mm-hmm.
And you can see the fluid kind of crawling up the walls of the tank attached to the veins.
Yes.
And you can see the center sump there.
Yes.
That's what they're doing.
Okay.
So you can see, right, there's the gas line here up top, and then there's more of the veins here.
Okay.
You can see it better now?
Yes. Yep, I can see that.
And this here is a mesh channel on the side.
Okay.
Mesh works better for cryogens, for I recall, than veins.
Okay.
I think I brought this up with Orbital Express, which we recorded like a year ago at this point, where we talked, my teammate talked to the guy who wrote his PhD thesis, which was 800 pages long, about cryogenic resupply systems for space missions.
Gosh.
It's all fluid mechanics. It's all satanic. And it's all fluid mechanics. But you can see, especially in the right image, like how it's just clinging to that central pillar.
It's glooping down, it looks like it.
And it's just water with blue food dye in it.
That's water?
That's water. Yes.
And it's acting like syrup.
Yeah. Isn't that cool?
That's crazy.
That is fluid mechanics in microgravity. This is where, like, remember we talked about like the nuclear forces, like the Van der Waals forces, like microfluidics in like high school? Mm-hmm. That's what's happening here. You're talking about...
Yeah,
like,
I definitely remember that.
Yeah, of course. Yeah, I remember it.
Of course you do.
But yeah,
that is insane.
Yeah, but isn't that cool?
That is awesome.
Again, you can see more. Again, I just got a lot of pictures of this. But you can see how it's just kind of climbing up the walls, what it's attached to, kind of where the bubbles are. And this does look like the meth that Walter White was making.
Yeah. It just turns the camera around and it's Bryan Cranston there going, "Come on, Jesse.
Yeah.
Look at this purity." Yeah,
every camera shot is like a process shot, like the weird
POV
ones.
Yeah. Put a camera on the inside of that.
Yeah, as they're filling it in and out. It's like, wow, this is order some nice music. But yeah, so you can see they got the channel here. And it's just, again, it's just kind of climbing up the walls.
Yeah, it's climbing up the walls. It's like mostly centered around the, gosh.
Yeah, but you can also see, so there's the big bubble. That's the ullage bubble, right? That's just the spare gas that's in the tank.
Yeah. Yeah.
And
you see, it's just a tube in there, though.
Yeah.
Like looking at the, yeah.
Yeah, and that's just how you transfer it. You just apply pressure and it flows out.
That's crazy.
Yeah, it's really cool though, and it looks more like water in these shots than it does in the others.
It looks like your classic '90s sci-fi fluids.
Yeah,
I keep thinking about The Rock.
I have never seen The Rock, but I know what you're talking about.
Okay. Yeah, you know the movie with
Sean Connery, right?
Yeah.
Michael Bay film. Yeah.
And Nicolas Cage.
Oh, yeah. That sounds like the greatest movie ever made.
It's a wonderful movie.
Okay.
But it has like the green. Like,
Yeah, I know.
like-
I know what you're talking about. It's like the
Yeah,
green
it's like-
spheres. Yeah.
those green spheres. That's what this reminds me of. But this is cooler.
This also kind of reminds me of the in Event Horizon, like the hibernation tubes that everyone was in.
I've never seen a Event Horizon.
Well, if you've seen Event Horizon, the crew to go to Neptune, they have to like crowd like sleep chambers, and it's fluid, so it looks kind of like this.
Oh, okay.
Kind of reminds me of. And of course, you got the cylinder with a bunch of bubbles in it,
Yes.
and more bubbles, which I like that shot there.
That's cool. Are those like bubbles inside of bubbles, or are those just reflections of bubbles?
That's bubbles inside of bubbles. Because remember,
Oh.
microgravity.
This is like one of the coolest images I've ever seen.
This is what makes the space shuttle program worth it. It's shots like these. Yeah, so because they're testing to see how like well vapor disperses when they're doing propellant transfer as well. Because again, if you're doing something for like a satellite in deep space, like Cassini, right, where you're waking up the engine after like 6 years in space, you're gonna have bubbles. What happens if you have vapor go into the engine? How do you make sure vapor doesn't go into your engine? Because it's gonna disrupt thrust and blow up the engine.
Do nasty things.
Nasty things are gonna happen to your engine. But yeah, look at that. That's
So cool.
It's so cool. And of course, on the right, you have more fluid clinging to the vanes as it's filling up.
Yeah.
What a cool experiment!
This is an awesome experiment.
Yeah, there's more. Okay, I forgot about. Again, this is the reason I picked this mission.
With this lighting, with this coloration, it looks a lot more green. It looks like flubber.
Yeah, we're just referencing a bunch of stuff in the '90s now, aren't we?
Yeah. This is classic 90s.
Yeah. And again, you can see the microfluidics happening. You can see it's connected to the veins, especially. And again, it's just connected to the sump.
Yeah.
That's just
It's clinging to it.
yeah, because it's microgravity. Gravity isn't going to pull it away. It's the van der Waals forces that are holding it there.
Yeah.
Surface tension,
Exactly, yeah.
which is it's important if you want to do stuff like propellant transfer in space.
Gotta know how fluids work.
Yep. So here's Duffy at astroculture.
Astroculture. Looks hype in there.
Oh yeah, and then that is a night vision shot of the shuttle.
Oh, okay. I thought that was like the inside
No,
of the astroculture. It's like
I'll get you low, from the outside. He's looking at this night vision,
yeah.
Yeah, this is I think the last mission photo I have. So,
Okay.
so the mission lands on July 1st, 1993 at 8:52 in the morning at Kennedy Space Center.
Just in time for work.
Just in time to clock in. This mission lasts 9 days, 23 hours, and 44 minutes, also known as 155 orbits.
It's a long mission.
Yeah. This mission is a great success. Nothing
Yes.
goes wrong. It's just another one of those mid-90s science flights under our belt, and it's got a really cool fluids transfer experiment.
With some of the coolest images ever.
Absolutely. Eureka never flew again. It's now in the Swiss Museum of Transport. You can go if you're ever in Switzerland, go to the Museum of Transport. You'll see Eureka, and they'll just start shouting, "Protein crystal growth experiments, count dust," and then they'll shoot you.
Well, no, it's Swiss. They'll
Oh.
bury you under one of the mountains.
Oh yeah. Also, what's interesting is when the crew landed, they were pretty much they got taken out, got taken to mission control, and talked to STS-51 crew, which is the first time those two that's ever really happened, where crews talk to each other like that.
Really? They don't talk. They don't mingle. They don't have a forum or something.
Well, they mingle, but they're talking as crews to each other.
Oh,
Yeah, which is interesting.
that's strange.
Yeah, I can't remember the specifics of what they were doing. I think it was like a dress rehearsal or something like that for STS-51, but
Oh yeah, because STS-51 was next.
is next. That one has IMAX shots, by the way. Some really good IMAX
Whoa.
shots. Yeah,
Okay.
yeah, that's a TDRS deployment too.
Oh.
Yeah, so the crew comes down. It's a mission.
We did it!
So Fair 2 achieved 85% of its goals.
That's a B.
That's pretty good. So it did vane control of liquid center of gravity. It did control of vapor-liquid motion under low gravity acceleration. So we're talking 10 to the minus 4 Gs.
Pretty low. It's pretty low.
Yep. A vane could expel gas-free liquid. The screen is better for that.
Okay.
Critical flow rate and Weber number were found for this. So what's the best way to make this flow, the fluid flow out of this before things start going wrong?
Mm-hmm.
And the Weber number is related to that. It's right. It's like Reynolds number. It's a non-dimensional number, so you can replicate things over different experimental setups.
Oh, okay.
It's like it's pretty much it's non-dimensional, like drag coefficient, right? It's just a number.
It's just a number.
Yeah, but but if you look at like a Reynolds number is like it's like dynamic viscosity divided by velocity, because that cancels out the units of the viscosity and the velocity. It makes a non-dimensional form of it. So if I have a lab that can make velocities really high, but you don't, you can change the viscosity of the fluid to replicate the Reynolds number.
Oh, okay.
Yeah.
Okay.
That kind of thing. You see it a lot in engineering and science because it's easy to replicate things and it's easier to make equations.
Cool.
So they did vent and repressurizations. They tested those. They're not as applicable to cryogens because cryogens boil. But for satellites, which use hydrazine and NTO, which are room temperature storable and a bit denser than water, you can do that.
This is perfect.
This is great for it. And then they did some 3D CFD modeling to correlate this. So this is actually a CFD model of the vane system. And you can see how old the computer stuff is because it's a bunch of triangles. Right, yeah. You can see those. That's it. And then Shoot demonstrated that vanes are better than meshes. Okay, I was wrong. And it could perform. it was one or the other. Okay.
Well, you had a 50-50 chance, and you threw heads.
I knew one of them was better than the other. Okay.
Again, you had a 50-50 chance you were wrong.
Details. I know where you live. I
know where you live.
I'm gonna fluid transfer something to your house, okay, buddy?
That sounds gross. Don't say that.
That is actually quite disgusting. This episode has been banned in the UK.
Cool.
So Shoot demonstrated that vanes are better than meshes, apparently, and it could perform transfers within 3% accuracy.
Nice.
Which is pretty cool. Now, there are some benefits to this, because SpaceX has to do this late next year for HLS.
They're definitely going to do that. I have faith. I believe.
They're gearing up for another flight, I think around the time this episode comes out. So we'll see if they're going to be on track for that.
I believe. When has Musk ever been wrong?
You know that Tesla opened up their own diner?
Yeah, I heard that.
It's got epic bacon because Elon hasn't aged since 2010.
Yeah.
Also, I think they violated food laws by storing stuff outside. So, yeah.
Classic.
Yeah, but that is STS-57. Yay!
Yay!
Fluid transfer experiments. Woo! The only reason I picked this mission.
It's a great reason.
It's a very good reason to pick this. And it'll do. And Fair 1, of course, is basically the same thing. So when we get to STS-53, that'll be really cool. And I know one of the other, I think STS-50s has a transfer experiment in the gas cans, and there's video of it.
Okay, yeah.
Yeah, I'll find those. It's like, again, it's all public domain, so I gotta go find those. I'll show you that for those. So on the next episode, we're going to talk about a mission where propellant transfer is very, very important to consider. Mars Observer.
Yay.
Woohoo! Any final thoughts on STS-57?
Dang, really cool.
Yeah, that's
bring polos back as well.
It's a really, really cool mission.
Yeah.
Yeah, fluid transfer experiments in space are always cool.
Fluids do weird stuff in space. Yeah.
That they do. I think that's everything. Hopefully the audio is fixed. If not, I'm gonna fluid transfer something into myself.
What?
What? I don't know.
It sounds like you're gonna take a drink.
Yeah, I don't need one. I got me some of Grandpa's cough medicine on my refrigerator. That'll make the next episode very interesting. STS-57, science.
Gotta love science. Thank you all for watching. Remember to like, comment, share, subscribe, and write nasty comments about the audio.
Mm-hmm.
And this has been End of Mission.
Woohoo!